As aircraft performance improved, early wood fabric wire structures became inadequate to meet increasing demands for higher speed, greater payload, longer range, and improved safety. The rise in engine power and operational loads exposed the limitations of wooden structures, such as poor fatigue life, sensitivity to moisture, and limited strength. To overcome these issues, aircraft designers began exploring metal as a primary structural material, marking a major transition in aircraft structural design. The earliest use of metal in aircraft structures involved steel and aluminum used selectively rather than for complete airframes. Steel tubes were initially employed in fuselage truss structures because of their high strength, while fabric coverings were retained to minimize weight. These hybrid structures represented a transitional phase, combining the familiarity of fabric-covered designs with the superior strength and durability of metals. With advances in metallurgy and manufacturing techniques, fully metal aircraft structures began to emerge. Aluminum and its alloys replaced wood in primary load-carrying members such as spars, frames, and longerons. The shift to metal allowed designers to achieve better dimensional stability, higher strength, and improved resistance to environmental degradation. This transition enabled aircraft to operate at higher speeds and under greater structural loads. The development of metal structures led to the introduction of new structural concepts such as monocoque and semi-monocoque construction. In monocoque structures, loads were carried mainly by the external skin, while in semi-monocoque structures, the skin worked together with internal frames, stringers, and bulkheads. These concepts significantly improved load distribution and structural efficiency compared to earlier truss-based designs. Metal aircraft structures offered several advantages over earlier designs, including higher strength-to-weight ratios, improved fatigue resistance, and greater durability. Metal skins provided smoother aerodynamic surfaces, reducing drag and improving performance. Additionally, metal structures were better suited for pressurized cabins and could be manufactured with tighter tolerances, leading to improved reliability and consistency. The adoption of metal structures fundamentally transformed aircraft design. It enabled higher cruising speeds, increased payload capacity, longer service life, and the introduction of pressurized cabins for high-altitude flight. The development of metal aircraft structures laid the foundation for modern airworthiness standards, fatigue analysis methods, and damage tolerance design philosophies used in contemporary aircraft. The Junkers J-1, developed in Germany during World War I, is widely recognized as the first practical all-metal aircraft. Designed by Hugo Junkers, it represented a revolutionary shift from traditional wood and fabric construction to metal aircraft structures, laying the foundation for modern aluminum airframes. The J-1 demonstrated that metal could be successfully used to achieve higher strength, durability, and reliability in aircraft design. By the early 1910s, wood and fabric aircraft had reached their practical limits in terms of speed, durability, and load capacity. These structures were highly sensitive to moisture, temperature changes, and fatigue. Military requirements during World War I demanded aircraft with greater structural strength, improved survivability, and longer service life. This need drove the exploration of metal as a primary structural material. The Junkers J-1 was constructed almost entirely from steel, including the fuselage, wings, and control surfaces. At the time, suitable aluminum alloys were not yet widely available, so steel was chosen for its high strength and availability. Although heavier than aluminum, steel allowed the aircraft to withstand higher aerodynamic loads and provided excellent resistance to battle damage and environmental degradation. The aircraft featured a cantilever wing design, eliminating the need for external bracing wires and struts that were common in wood and fabric aircraft. Loads were carried through a metal framework and stressed skin, marking an early form of semi-monocoque construction. This design significantly reduced aerodynamic drag and improved structural efficiency, even though it increased overall weight. Manufacturing of the Junkers J-1 involved metal forming, riveting, and welding, which were advanced techniques for the period. Corrugated metal sheets were used to increase stiffness without excessive weight. Unlike handcrafted wooden airframes, this approach introduced the concept of repeatable, industrial-scale aircraft production, which later became standard practice. The operational performance of the Junkers J-1 demonstrated the feasibility of all-metal aircraft construction. The aircraft made its first flight on December 12, 1915, and was configured as an all-metal monoplane with a single pilot crew. Although the Junkers J-1 did not enter mass production due to its relatively high structural weight, it flew successfully and conclusively proved that metal airframes could be structurally sound, durable, and capable of sustained flight, thereby validating the concept of all-metal aircraft structures and influencing future aircraft design. The Junkers J-1 directly influenced later aircraft such as the Junkers J-4 and paved the way for aluminum alloy structures in the 1920s and 1930s. Its cantilever wing and stressed skin concepts became fundamental to modern aircraft design. The transition it initiated ultimately led to high-performance aircraft capable of long-range flight, high speeds, and large payloads.